And you take your delta t and you take the limit as it goes closer and closer to 0, this thing becomes dt. That's our notation. So we took this and we morphed it into this. These mean the same thing, but you can't really add up a number of infinite ones. So this kind of says this. And we call this, okay? This is how to calculate the area. We're going to see how to do it here in a moment. But this is what I want to talk about. When I'm over here, and I'm moving down in this direction, I look at here, I take the slope to get down here, I take the slope to get down here, and now if I want to go back, I take the area. So the way we express this we say that the area is the anti-slope, because area takes you from position and velocity to acceleration, and then the slope takes you from position to velocity and velocity to acceleration. The anti-slope then takes you from acceleration back up to the change in velocity, back up to the change in position. It's the anti-slope. So when you see this notation, this thing here means take the anti-slope of this function to get the change in velocity. It's just the area. How do you do it mathematically, though? That's the real question. And this, I think, is the most fun part, is that it's actually quite easy to do using our conceptual framework. When we had the slope algorithm that we talked about before, I'll write it down in terms of the velocity. So if we were given a velocity function in a general form that looked like the velocity is equal to some coefficient a times t raised to the n power, how did we use the slope algorithm to get the acceleration? Well, we had two steps. Step number one, was to multiply the coefficient by the exponent, and then subtract 1 from the exponent. No problem. If I do that here, apply these two, that means my acceleration function is equal to that's the algorithm. Well, now what I want to do is I don't want to use the slope algorithm, I want to use the anti-slope algorithm. And the coolest thing about it is the anti-slope algorithm is you do the same two things, but because it's anti, you do them opposite, and you do them in the opposite order. So the anti-slope algorithm opposite thing in opposite order. You're going to add 1 to the exponent, and then opposite thing in opposite order. You're going to divide the coefficient by the new exponent. So let's see what that looks like. I'm here, I'm going to add 1 to the exponent, and then divide. But since we're doing anti-slope, that's going to be my change in position, because that is the area. This area says take the anti-slope algorithm of this function. So, the steps are reversed. It's the opposite thing in opposite order. Add 1 to the exponent, divide the coefficient by the new exponent. How does that actually manifest? Okay, how does that actually manifest? So let's go back to our original example from the day. Let's say that we look at an object and our velocity function is as follows. Well, let's say that it's given to us that the velocity function is equal to 6t squared. The velocity function is equal to 6t squared. And then we're asked to do two things. One, we're asked to figure out a function for the acceleration. And we're also asked to figure out a function for the change in position of your object. I think we can do both pretty easily. Let's do the easy one first. If I want to get the acceleration, I'm going to apply the slope algorithm. Slope algorithm says multiply your coefficient by your exponent and then subtract 1 to get the new exponent. No problem. Acceleration is equal to, take my coefficient, multiply that by the exponent. 6 times 2 is 12t, which totally makes some sense to me, right? Because I subtracted 1, 2 minus 1 is 1. What this tells me is that it's linear in a y equals mx plus b fashion. So now I have a function for this, and I can get a sense of it. And we know if you're a parabola, the slope of a parabola function is linear, which is so cool. What about the change in the position? This is the hard one, right? We have to apply the anti-slope algorithm. The anti-slope algorithm says add 1 to the exponent and then divide the coefficient by the new exponent. Well, let's do that. If I add 1 to the exponent, 2 plus 1 is 3. And then divide by the new exponent, which is 3. And so my change in position function, 6 divided by 3 is 2t cubed. Now, this doesn't exactly give me the position function. What it gives me is the change in position function. So if I added x0 to both sides, I could end up with the actual position function is equal to and if I knew the x0, for example, let's say the x0 is 0, I'm going to end up with a nice cubic function. And that function is 2t cubed. And so we have the cubic function, the squared function, the linear function, and that's pretty consistent with our understanding of how these graphs work together. That's enough of that.